So we've talked about the information that we can extract from stars. I want to take a little time, however, to talk about what that light has to pass through in order to get from the star to our telescopes on and around Earth. So we're going to talk about the interstellar medium.
So when we look out into the night sky, we see an awful lot of stars, but there is just as much mass out there in gas and dust, which we usually do not see directly. As we'll see, dust is what astronomers refer to as very small microscopic clumps of molecules. Most of the gas and dust out there we infer because of its effects on starlight. So let's talk a little bit about those effects. Take the blue sky on a sunny day. The reason the sky is blue is due to a famous effect called Rayleigh scattering. Light gets scattered off particles that have a similar dimension to the wavelength of that light. The molecules that make up our atmosphere are about the right size to scatter blue light particularly well, with yellow and red light scattered less efficiently. The result is that if the sun is high above you, blue light scatters in all directions, yellow and red light make it through, and the sun appears yellowish. If you look away from the sun, the sky appears blue because all of the blue light from the sun has been scattered off in every direction. So that's what you see when the light doesn't actually have to travel through that much atmosphere, when the sun is directly above you. If the sun is low on the horizon, however, say you're watching a sunset, then the light from the sun has to pass through a lot more atmosphere. In that case, most of the blue light never reaches you. It is scattered so efficiently. And that just leaves the red light, which itself is scattered more than it would be if you were looking directly up at the sun. The result is that the sun appears redder and the sky around the sun appears red. The bottom line is that the more atmosphere, the more gas the light travels through, the redder that light will appear. Also, the sun appears dimmer at sunset, once again because more light is scattered away from your line of sight. So there are two effects going on here, extinction and reddening. The more gas light travels through, the dimmer it gets and the redder it gets. And this is true for starlight traveling through the much, much less dense interstellar medium, the gas and the dust that exists out in space. Take a star on the left. It emits light. It travels many light years, maybe many hundreds or thousands of light years, through all of the dust and gas in between us and the star. Blue light will be scattered out of our line of sight, so the object, once it gets to us, will appear redder than it did before. We've also lost a lot of light because it's been scattered out of our line of sight by gas and dust. So our blue star, which appeared quite bright, now appears dimmer as well as redder. Near the sun, extinction amounts to about 2 magnitudes per 1,000 parsecs. That is, a star 1,000 parsecs from the Earth will look about 2 magnitudes fainter than if space were completely empty. Most of the dust is thought to come from stellar winds. These are outer layers of stars being blown off because they are just about on the limit of stability. Remember the virial theorem for massive stars that are supported by radiation pressure. The outer layers of these massive stars are pretty cool and blow out molecules of hydrogen and carbon and other elements that cool and coalesce into dust grains. If you plot the extinction, how well the dust scatters light away from our line of sight versus wavelength, then as one moves to higher wavelengths, in other words bluer light, the extinction increases. Bluer light is scattered more efficiently than red light. And indeed, there's a hump in this extinction curve, and that hump is caused by grains of carbon in dust. Very efficient at scattering light in the near ultraviolet. Here's a little cartoon cross-section of a typical dust grain. They're very, very small, microscopic. 100 nanometers is a typical size. They may be coated in water ice, but they contain a lot of carbon and silicon in the center. So much of the gas and the dust out there we don't see directly, but we see because stars appear dimmer and redder than they actually are. How do we know they're dimmer and redder and not just less bright, redder stars? Well, because we have several ways of measuring their distance. If, for example, we measure their distance using spectroscopic parallax, where we get an idea of their temperature from the spectral lines that we see, that's a method of measuring distance that doesn't rely on us knowing how bright the stars are. So we can compare that distance to the distance that we get by figuring out how bright the star appears to be. If the star is fainter than it should be for the measured distance, then that allows us to estimate how much extinction there is. Now, most gas and dust in our galaxy lies in the vast amount of empty space between stars, but some of the most spectacular examples of dust and gas clouds come from those clouds that are close by stars, which result in some directly observable phenomena that are generally referred to as nebulae. Here is an example of the Rosetta Nebula, and this is the first type of nebula we'll discuss, an emission nebula. So what you're seeing here is gas surrounding stars that is emitting light, and the light from the gas is light from an emission spectrum. Now, just a reminder, emission spectrum is the result of a low-density gas that is excited to emit light at specific wavelengths. In this case, the gas is excited by light from hot stars. So all the bright stars in the picture here, a lot of them are massive stars with surface temperatures of more than 25,000 degrees Kelvin. That light hits the atoms in the gas cloud, causes electrons in the atoms of hydrogen that make up most of the gas cloud to jump up a level, and when they jump down, they emit light of specific wavelengths, and that is what we see. It's important to note that the gas here is not generating its own light. It is merely being excited by the light from the stars. Now, because it's being constantly bombarded by light from these hot stars, most of the hydrogen is actually ionized, and these regions are called H2 regions because H2 is the name given to once ionized hydrogen. The density of gas here is around 100 to 1,000 atoms per cubic centimeter, which kind of puts things in perspective a little bit. This is orders and orders of magnitudes a better vacuum than the best vacuum that we can produce on Earth. Yet the distances and volumes are so large that there's still enough gas there to produce these exciting and beautiful images. The region it tends to be pink and is due to a mixture of the Balmer emission lines from hydrogen, which are red, blue, and violet. Mix them together and you get pink. So you can tell an emission nebula because it will appear pink. A couple of other examples of emission nebula are the Eagle Nebula and the Orion Nebula. Okay, the next type of nebula is a reflection nebula. So as the name suggests, light here is being reflected or scattered by dust and gas, much like the moon reflects the sun's light. So again, it's not generating its own light. It tends to scatter light from cooler stars than emission nebulae, so the light isn't energetic enough to excite the gas. It appears blue for the same reason as our sky appears blue. These gas clouds tend to contain a lot of dust, which does most of the scattering of the light. One interesting thing is that because the light from the stars are reflecting and scattering off of the gas and then making their way to our telescopes, the light still contains the absorption spectrum of the star. So if you measure light from the nebula, you'll see absorption lines, and those absorption lines often come from the star itself. So you can figure out information about the star by looking at the light that is reflected by the gas and the dust. Those spectral lines tend to be broadened because of the random motion of the gas molecules that are doing the reflecting. And that tells you something about the speed of the gas molecules in the cloud, which tells you the temperature. We can even tell whether the light has traveled through more than one different gas or dust cloud. That will tend to Doppler shift the light to different extents because different gas clouds will overall be moving with different velocities. Okay, the third type of nebulae are dark nebulae. So these are more dense clouds of dust and gas, and they don't emit light, they don't reflect light, they don't get excited. What they do is they just get in the way of light from background stars and obscure it. Dust clouds tend to be very cool, 10 to 100 Kelvin. Some famous examples are the Snake Nebula and the Horse's Head Nebula in Orion. In fact, the Horse's Head Nebula, as you can see here, actually contains examples of all three types of nebula. You get the pink emission nebulae, blue reflection nebulae, and the dark nebulae. So overall, the gas and dust is called the interstellar medium, but it's not the same everywhere. There are different types of clouds, different ways that the gas can clump together. So astronomers have organized the various components of the interstellar medium according to their physical properties and composition. H1 clouds are typically seen through interstellar absorption lines and 21 centimeter radiation. Interstellar absorption lines, as the name suggests, is when the hydrogen in the H1 clouds, which, as you should be able to tell by now, is neutral, absorbs light at very specific frequencies from background stars, causing characteristic absorption lines. We also see it through 21 centimeter radiation. The figure on the right illustrates what this is. This is when hydrogen atoms bump into each other. They can cause the spin of the electron to be aligned with the spin of the proton. In other words, they'll both be rotating, say, clockwise or counterclockwise. This is a higher energy configuration than if the electron spins in the opposite direction to the proton. So what happens when they're in the high energy configuration is that the electron can flip its spin, and that causes it to release energy at a very specific energy, which turns out to be a wavelength of 21 centimeters. So this is the cast iron signature of interstellar neutral hydrogen. These clouds tend to be between 50 and 150 parsecs in diameter. Just to put that into some perspective, there are about 100,000 stars in the 50 parsecs closest to the sun. So this is a huge volume of space, although it's not very big compared to our galaxy. The temperature of the hydrogen is around 100 degrees Kelvin, and the density is about 10 to 100 atoms or molecules per cubic centimeter. Again, it's incredibly diffuse. The shape of the clouds tend to be filament-like. If these clouds get near hot stars, the hydrogen gets ionized to form H2 regions, which we saw cause emission nebulae. The second component is really two components, which I'm lumping together, the warm or hot intercloud medium. So this is just the stuff that exists between H1 clouds. As the name suggests, it's a lot warmer than the H1 clouds. Temperatures of the hydrogen atoms get up to a few thousand degrees Kelvin, but it's much, much less dense. On average, you've got 0.1 molecule per cubic centimeter. So that means you'd have to take the volume of, say, a mug of coffee before you would find even a single molecule or atom of hydrogen in there. So this is mostly H1 atoms or molecules or ionized hydrogen, where the H2 is ionized by ultraviolet light from stars. The third component are giant molecular clouds, or GMCs for short. These contain larger molecules, which are sometimes organic, although they're still mostly hydrogen. They're very, very cold, around 10 degrees Kelvin, and a lot denser than H1 regions or the warm or hot intercloud medium, 1,000 to 100,000 molecules per cubic centimeter. They tend to be around 15 to 60 parsecs across, and these are the things that are often seen as dark nebulae. So we've seen some examples of these before. The famous Pillars of Creation, one of the first really famous Hubble photographs, are giant molecular clouds. Here's a nice high-resolution close-up on some giant molecular clouds. So these are dark nebulae. We see them because they are obscuring light from behind. As we'll see, it is these clouds that will collapse to form new stars. Here are a couple of other pictures of giant molecular clouds. And just to give you a sense of scale, this dot here is our entire solar system in comparison. They contain a lot of organic molecules. Because they're so cool, molecules can form. They're not bumping into each other very energetically, so they're not going to fall apart. And so far, we've detected many, many organic molecules in these giant molecular clouds, of which this is a very incomplete list on the right here. The fourth component is coronal gas. This component is very hot, 100,000 to 1,000,000 degrees Kelvin, and very, very diffuse, about 10 to the minus 3 to 10 to the minus 4 atoms per cubic centimeter. So in a liter of space, you would find about an atom. This consists of ionized hydrogen chiefly, which comes from supernovae or other very hot stars, and it's hot enough that it emits X-rays. The name is confusing, as is often the case in astronomy. It has nothing to do with the sun's corona, although the gas from the sun's corona is similar. Here is an artistic impression of a map that we've been able to make of the gas in our solar neighborhood. The yellowy orange gas that you see is coronal gas. The sun is roughly at the center of what appears to be a bubble. Here are some of our nearby stars. Here is another picture here. This is called the local bubble. The space inside of this bubble of hot coronal gas actually has very, very little interstellar medium, and it is thought that this entire region of space was cleared of its gas by a supernova explosion or several supernova explosions about 10 million years ago. Of course, although this is very local to us by galactic standards, it is still an enormous volume of space, big enough that supernova explosions could go off without being close enough to damage life on Earth. So to summarize, we see evidence for the interstellar medium through extinction and reddening, emission nebulae, dark nebulae, reflection nebulae, 21 centimeter radiation, and X-rays from hot gas between stars. And we've been able to use these observations to figure out the basic components, the constituents of the interstellar medium. H1 clouds, the warm and hot intercloud medium, giant molecular clouds, and coronal gas. It is this gas and dust from which new stars are born.